Hi, we're Group 25. My name's Dave.
My name's Dave.
And I'm Kai.
And we're doing an electric vehicle charger for both fully electric vehicles and plug-in hybrids.
Okay, so the motivation for the intelligent vehicle charger arises from a need to control the flow of power during peak hours. When everybody gets off work at the same time and comes home and tries to plug in their vehicles, the grid can't handle charging every single vehicle at the same time. So there needs to be some intelligent way to divert some of that charging to a later time, or to delay the charging so that it cannot charge at the times that could damage the grid. In order to do that, we implement 3 separate ways to control the charging of vehicles. The first way is to allow users to set an alarm to charge their car at a later point in time. Somebody can come home when they get off work and tell it to charge at 11 o'clock or midnight in the middle of the night when the power usage is at its lowest, cheapest, and easiest for the power grid. The second way that we control it is have a wireless card embedded in our design, which allows communication with both power companies so that they can monitor the usage of power and turn off vehicle chargers, and consumers so that they can monitor their own power usage and regulate their own charging times. The third way that we have this set up is a frequency sensor that's built into it. This is a fail-safe. If the grid is undergoing a period of high stress where it's going to shut down or have significant problems due to too many people being on the grid at one time, then the entire project will actually stop charging based off the frequency of the grid. This is a very small change, but when the grid becomes stressed, the frequency changes just a little bit, which is enough for our project to detect and shut off charging.
So we want to show you guys our block diagram right now. I'm going to pull it up on the screen. You'll be able to hear my voice. The Branch Charger 4.0 has an intricate system level diagram. Starting in the bottom right, you can see the user. Now this guy has several ways of performing essentially the same function of opening or closing the solid state relay. His 2 options are either the wireless user interface or the manual user interface. Both of these operations go directly toward the brain of the operation, the Arduino controller. On-off functions are provided by the wireless interface and the manual interface, as well as the ability to set an alarm for late night charging. Now from the power perspective, we start on the left side of the diagram. Off of either the 240 or 120 center taps, we step down the voltage peripherals using a transformer and a buck boost duty converter to convert both 5 and 12 volt supplies to our LCD, real-time clock, the Arduino itself, and a fan circuit to keep our project running smoothly. We also sample the frequency of the grid, which is sent through a comparator to digitize the signal and allow us to do code side processing and generate a frequency to be displayed on the LCD.
Okay, our first unique design feature is our peripheral power supply. We did 2 unique things with this. The first thing we did is we had universal power input. This means that it would have to work with both 120 volts and 240 volts, which is a very important concept. The second thing that we've done that was different is we used a switch mode power supply. Seeing how we're doing a sustainable energy project, we decided to do a very energy efficient step-down converter so we didn't waste a whole bunch of energy. These things are known to be above 85% efficient, and ours was actually 97% efficient. Our first design, however, failed. We tried to use something that we've done before in our past labs, which is use a transformer to step down the AC voltage, and then rectify it, and from there we used a buck converter to bring it down to 12 volts. This actually worked. On 240 and 120 volts, it would work. However, we would have to change the wiring of the transformer. The transformer that we had to use for the 240 volts had 4 windings on each side and had to be put in series for 240 so we could get enough juice out of enough flux and we wouldn't have enough voltage swing. Or parallel in 120, so that 120 is applied across each winding and we could pull enough flux to pull the current that we needed out. Now that sounds very confusing. What that means is that we would have to change the wiring on the transformer. Because if we had it set up for a 240 volt winding and put 120 volts across it, we would lose voltage and lose energy due to the higher resistance. And then we wouldn't get enough power out, and we would only be able to supply about half an amp when we needed about 3/4 of an amp. If we wired it for 120 and supplied 240, the extra voltage across the resistance would heat up the transformer, and the core flux would maximize, and we'd get a whole bunch of smoke coming from the transformer. So that was our main consideration.
Another unique feature of our design was the Arduino Uno microcontroller. Now what makes this thing beautiful is that it has its own programming language, It has its own built-in hardware and is extremely well documented. In fact, if you're on a team right now and you don't have a controller guy on your team, I suggest using the Arduino Uno interface, and this is why. The controller comes with a built-in serial to USB interface. This allows you to bypass those pesky programmers and use a USB cable to program your Arduino very quickly, very efficiently. It comes with several interrupts, and this allows you to do any kind of digital processing you might need to do very efficiently and very quickly. And also it comes with a couple of shields. We bought a wireless shield for our project, which allowed us to communicate wirelessly. There's also things like LCD shields and real-time clock shields. There's basically anything that you might want to design into your project, there's a shield for it already. This is very helpful when you're trying to save time. As a matter of fact, the hardest thing sometimes, especially in senior design projects where you have other classes and other things going on, is time saving. What's beautiful about the Arduino is that someone has already done the project, someone has already gotten it done, so they've already made a tutorial, they've already documented it. These are accessible online. It's an open source database. And we were able to implement some of our projects in a matter of hours when it normally would have taken dozens.
Our fourth unique feature is wireless communication. Wireless communication works by allowing the user to specify trusted networks and passkeys using WEP, WPA, and WPA2 encryption. Once this is done, whenever the device is turned on, it will automatically try to connect to the closest local trusted network. When this happens and the connection is made, the device will act as a TCP host that is accessible by a TCP client from anywhere on the web. This is especially unique because it allows more direct access from the device to the router to the web, as opposed from the device to a user's computer and then to the web. This essentially cuts out the need for a user to have either their laptop or desktop running whenever they need to access the device wirelessly.
So we want to give you guys a demonstration of our project. This is the branch charger. It's a beautiful charger. As you can see, it fits into a briefcase. Makes it portable. You can put it in your trunk, carry it with you wherever you want to go. We basically provide 4 different functions. Start charging, stop charging, check frequency, and set alarm. Originally, we had all of these functions on the same screen with no menu. That was impossible to navigate. There was no way to get all the functionality in there. So we reduced it to a 3-button menu system. Enter, up, and down. And I'm going to demonstrate how it works for you. As you can see, as I push the down button, the cursor jumps down. And as I push the up button, the cursor jumps back up. We also use 2 different inputs for our design. A 240 line and a 120 line, which is plugged in right now. As you can see, I press start charging, and you can hear it start. I go to stop charging, and you can hear it turn off. Frequency, checks the frequency. As you can see, it's reading an accurate frequency of 60.4. So I want to show you the alarm. Basically, you can see our real-time clock functioning appropriately. As you can tell, we procrastinated. It's 11 o'clock at night. And you can see that as I push these buttons, the hours and the minutes are changing. This is the hour button. Let me set the alarm for you. It'll take about 10 seconds for this to cycle. So as you can see, I press enter, it's set to go off. And as it cycles, you can see the time goes off and it starts charging. Since the power is being supplied right now, I should probably stop charging. And just as a final act of our demonstration, I'd like to show you how portable exactly it is. Set the breaker off. Plug. Cord. Got a charger. So we're group 25. This is our intelligent vehicle charger. We have some suggestions for you incoming seniors. Starting with Dave.
My suggestion for incoming seniors is that they really think out their initial requirements first term and make sure that they're reasonable and attainable in the terms to come.
If you have a design choice between something that's well documented and something that's not, choose the well documented item, even if it's a little more expensive.
And keep in mind that everything is going to take a lot longer than you're going to expect. When you do encounter errors, make sure that you debug them accurately. Find the problem and fix it. Don't just randomly go at it.